In this video, we'll continue talking about the applications of maxima and minima from the previous one. So I just wanted to concentrate a little bit more on the last few examples as they're a little bit more involved. So let's take a look at this one. Your underground used book business is booming. Again, I'm not sure about the legality of this, but textbook publishers tend to frown upon that, so just keep that in mind. But your policy is to sell all used versions of Calculus and U at the same price, regardless of condition. How nice. But anyway, when you set the price at $10, and that actually applies to any business situation, maybe we'll have a little bonus assignment doing something similar. But when you have two different price points, but then you keep track of how many you sell at each different price point. So let's say $10, you sell 120 books, but at $30, maybe you don't sell any. So it drops to 0. So you already have 2 points in terms of price and quantity, so you can actually figure out the demand. That's how you can do this for any business, actually. So the following semester, you set the price at $30. I think I already mentioned this, and the sales drop to 0. So the demand depends linearly on the price. What price gives you the maximum revenue, and what does that revenue amount to? So here we need to recall linear equations from chapter 1, very beginning of the course. So if your demand, which I'll call Q for the quantity, but it's really almost like Y equals mx plus B, if you remember from before, but it's Q of P. I just again try to be consistent with variables equals to M times P plus B. So it's a linear equation where P is the X, the price is your X or your independent variable, and your quantity depends on price, which is your Y. So we have 2 points. So since P is your X, we're going to have that point first, and then Q is your Y. And you can write them as 2 points, 10, 120, and 30, 0. And if you recall, you can use the 2 points to find both slope, which we do in this case, 0 minus 120 over 30 minus 10. So we get negative 120 over 20, which is negative 6. And I tried to use one of the points, let's say 30, 0, to write the equation of the line. And notice I go through these steps. So I get Q equals negative 6P plus 180. So that's our demand function, which then in turn we can build our revenue, which is price times quantity, and substitute this Q equation inside of this Q and distribute the P. So we get negative 6P squared plus 180P. Again, once again, note that this is an upside down quadratic. It would have a maximum. So that's how you can do this. In fact, again, very applicable for any business situation. But we can take the derivative, which is negative 12P plus 180. Once again, set it equal to 0, solve for P. So you get P equals 15. So it's actually definitely less than 30, but a little bit more than $10. And so I use $10 and I use $20 to check, make sure it's a maximum. And it is. And then you can plug in 15 into your revenue equation, which is negative 6P squared plus 180P. And I get $2,565. So not bad for the underground textbook business, assuming you have a lot of them to sell. And that's it for that problem. Now I want to do a little bit more volume, couple more volume problems in this section. And let's say a packaging company is going to make closed boxes with square bases that hold 125 cubic centimeters. What are the dimensions of the box that can be built with least material? So again, it helps to draw a little picture. I drew a little cube. It took me some time, but because it's a square base, that means the length and the width are the same. So I just call them X to make it easier. But then the height could be different depending on the box. So it doesn't really tell you that we have a volume, but anytime you hear cubic centimeters, so you can assume that we're talking about the volume unless it indicates otherwise. And volume for this cube, for the box, it's basically like the area if you talk about 3 dimensions, but it's length times width times height, which we can substitute. The length and the width are X, so that they're both X, so we get X squared times height, H, and it's 125. So I solved for H just because it would be easier to have everything in terms of X. So we get 125 over x squared. Now, this is the tricky part to set up the second equation, so pay attention to the one where you get it on the homework. I think it's the next to the last problem. But it says what dimensions of the box can be built with least material. So I'm assuming we're going outside of the box using the material, and just like the perimeter with 2 dimensions going outside of the box, the equivalent in 3 dimensions is called surface area, which you can look up, but I'll tell you the easy way to figure this out. So that's the equivalent of perimeter in 3 dimensions, essentially, surface area, and that's also going around the outside. How do you get the surface area? I called it S for the surface. Basically, if you add up all the areas of all the sides, we have 6 sides of the box, of each face of the box. And basically, because you have 2 faces for each one, the top, bottom, and all the sides, so I ended up with twice times length times width, so you have that top and the bottom, plus twice of the width times height. I think this is a couple of the sides, I think the front and the back, and then plus twice times the length times height. Those were the sides, the 2 ones on each side, sort of like east and west, I guess. And if we substitute basically length and width with the x's, and we keep the height as h, and which we can substitute, which we already found in terms of x as well. So just a little substitution. So again, it's twice of each area. If you add up, basically just keep track of each face. So because there's twice of each face, I just did the length times width, width times height, length times height. So if we substitute them in, we get 2x squared for the first part, then plus 2x times 125 over x squared, and same thing for the third one. And if we simplify, we'll get 2x squared, but then we have, I think I simplified it, you get 250 over x plus another 250 over x, so we can combine them into the 500 over x. And basically, we get this equation, 2x squared plus 500x to the negative 1 power. And that's our equation, the surface area. So it took us some work to get here, but now we're here. And then from here, taking the derivative, so we'll get 4x minus 500x to the negative 2nd power. Again, we can set it equal to 0 to find the minimum for the least material. So we'll get 4x cubed equals to 500. I think, again, I move the 500x to the negative 2nd power to this side. I put x squared on the bottom. They just multiplied both sides by x squared. And we end up with 4x cubed equals to 500. So go through these steps. Divide by 4, so we'll get x cubed equals to 125. So now you can find, well, you can actually figure out that it's 5 is a cube root of x, of 125, sorry. Or you can use your calculator. I believe it's math option 3 or something like that for the cube root, so you can look for that. So we can get 5 here. And once again, you can, I picked 4 and 6, again, something easy. To plug in back in the original derivative, which was 4x minus 500 over x squared. It probably helps to rewrite it like this. I paused the video and I basically put x squared in the denominator so it's easier to see. So here's where you can plug in 4 or the 6 to check for the sign. And anyway, that's happened to be a minimum. And so what are the dimensions that give us that minimum? We know x is 5, and we can plug in for the h to find the height. It also happens to be 5. So 5 by 5 by 5, it actually is a square box, actually requires the least amount of material. So that's just applying it again, area and perimeter all over again, just in 3 dimensions. And one more, maybe another volume problem actually. U.S. Postal Service will accept packages only if length plus girth, we'll define what that means, is no more than 108 inches. And you can see the picture, which is actually helpfully provided. It should be provided on your homework. And then assuming that the front face of the package is square, what is the least largest volume that USPS will accept? So girth is, I think, is going around the whole perimeter of the front face. In fact, I think the picture shows it if you go follow the arrows around. So going around the whole face, which will be 4x, the front face, so that's the girth, plus length. So it can be no more than, so what if we set it equal to 108 to find the largest volume box? So you want to set it to be the highest it can be. So it can be no more than, so we set it to exactly 108 to find the maximum. And once again, we have an equation where we can solve for one of the variables. I chose to solve for the length, which will get negative 4x plus 108. And then we can substitute it into the volume. So we're trying to find our largest volume or maximum of the volume. So that should be length times width, which is x times x, times the length is negative 4x plus 108. Once again, you can distribute. This time it's x squared. So if we distribute it, we'll get negative 4x cubed plus 108x squared. You can take the derivative. So we'll get negative 12x squared plus 216x. So again, because it's a volume, we'll have a cubed, but that's okay. And I think here we can pull out an x and to solve for 0. Well, x equals 0, but that doesn't make any sense. Then we would not have a box. Or x equals 18 if you solve the one in parentheses. And we can check to make sure 18 is a maximum. And I think it is. So again, you can pick something easy to plug in into the derivative, which is negative 12x squared plus 216x. Or actually in the factored version. Remember, you can plug in 16. And actually you get a positive. You plug in 20, you actually get a negative. And so you do get a maximum at 18 inches. So the final answer would be 18 is the length and width. And the height is, I think we found it earlier, negative 4x plus 108. So which would give us 36. And if you multiply them all out, you'll get 11,644 inch cubed. I believe we did ask what the question did ask what the volume was. What is the largest volume? And so we did find the dimensions. So it's not just the dimensions, but the actual volume that we're being asked to find. And so if you multiply them out, this is the volume that we'll get. And that's it for 5.2.